So we looked at this example of trying to determine if there's some connection between how the vehicle arrives at the intersection and whether or not they come to a complete stop. And we saw that there's two different statistics we could use to try and measure that deviation from expected. Here we looked at how they deviate from each other, and here we looked at how they deviated from the expected counts that we would have if everything matched the population values. So now let's look in the applet how we could simulate the null distribution and then get some sort of p-value on these statistics. So here I've got the data in, and just so things will look nice in the applet, I abbreviated. So I'm using SV for single vehicle, LV for lead vehicle, and FV for following vehicle, and then CS for complete stop, and NCS for no complete stop. And so here's our 400 cars in all the different combinations that we had from that table. Unfortunately, the applet does not set up for just putting in the counts. Now, for simulation, that's okay. For the theory, there's plenty of applets we could just Google that would allow you to put in a table of whatever dimension. So I'm doing this as actual paired data here, though, of the two variables. So we'll copy that. And then over in the applet, we want to do the multiple proportion. And you see what I mean? As a table, you can only really put in a 2 by 2. At least as far as I can tell on this applet. But if you go with data, I'll clear that, paste in our data, and then use data. The first thing we get is this nice segmented bar graph, so we can kind of see the difference in percentages. We're seeing some difference here. The question is that difference significant? And you can switch which variable is the one that you're calling success. You can flip that around. I was counting the proportions on the complete stop category, so I'll keep it as that. This is kind of nice. You can actually see the table. So it counted up all those categories, and this should match what we had for our table. It's kind of a nice check on our work there. Or if all you had was raw data, this gives you your counts. And then here's where you can select which statistic you're going to use. So we calculated both the MAD and the chi-squared. And if you look, this is what I got for my MAD statistic, 0.086. The chi-square value is slightly different. I got 8.4 when I did it by hand, and this is 7.4. There's going to be a bit of a difference because I was doing a rough calculation. I rounded all of those expected values to an integer. When the computer's calculating it, it's not doing any rounding. So mine's more of a rough calculation. That was just for demo purposes to make it easy. But here's the actual chi-squared value if you hadn't have rounded anything along the way. This is kind of nice. You can also show the chi-square output. Now, what are these numbers? Do you remember when I calculated chi-squared, we had all those differences between observed and expected squared over the expected? If we had computed what those individual 6 values are, here they are. So one way of thinking of them is these are the contributions, as is labeled right there. The bigger the number, the larger that cell deviated from expected as a proportion to what was expected. So this category right here has the largest contribution to our chi-squared calculation, whereas this cell has the smallest contribution. It's contributing barely anything to the chi-squared calculation because remember, chi-squared is going to add all these numbers up, and that's where the chi-squared, the statistic of 7.398 is coming from. So actually, this one cell is contributing over half of the total of that calculation. Okay, so lots of stuff you can look at here. Now let's actually simulate to get some p-values. So we'll come over here and show our shuffle options. Well, the logic of the shuffling is exactly the same. Let's just do one shuffle. What did it do? If we scroll through, there's the single vehicle stuff, then the lead vehicle stuff, and then lastly will be the following vehicle. It didn't touch those variables, and then it just randomly scrambled the complete stop and non-complete stop. So these are just randomly being associated to these guys. So you would expect there to be no connection between the two variables because the response variable is randomly assigned, and it just shuffled the responses that we had. So if we went back to our, all it's really doing is shuffling column B here. And then it computes, let's do the MAD first. So let me switch this back to MAD. So it went through and did the shuffle, and it calculated on this shuffle a MAD of 0.071, and it plotted it there. So there's one thing you might get if there was no connection between the two variables. And then it keeps doing that. We could do 1,000 at a time. Right now I've got about 12,000 shuffles. Maybe do 10,000 at a time, just do one more, get it up to 22,000 shuffles. And finally, for really the first time this semester, we're seeing a null distribution that does not look bell-shaped and symmetric. If you think about how the MAD is calculated, it's the sum of a bunch of absolute values. So the smallest it could ever be is 0. We get this distribution that jumps up right away and then has only a tail on the right because it can't go any lower than 0. This distribution, this shape is new to us. Okay, so what did we get? We want to calculate a p-value. So let's come back over. Our MAD was 0.086. So what would be the likelihood, if there was no connection in these variables, the likelihood of getting what we got or something greater? Pretty small. That would be significant at the 5% level. Not quite significant at the 1% level. If we wanted to make sure, let's just maybe do another 10,000 or so, see how much it changes. Now we've pretty much settled in here, 0.012. If I add in another 10,000 shuffles, yeah, that's updated. 0.012, it's not moving. So pretty significant. It would definitely be at the 5% level, we would definitely conclude that there's an association between these two variables, between when the cars arrive, how they arrive, and whether or not they stop. At the 1% level, we're not quite there. So we're not that confident, but definitely at the 5% level, we're confident that the two variables are associated. Okay, let's switch over so that our statistic is now, instead of the MAD, it's the chi-squared. And you'll notice the chi-squared distribution also, because if you think about how chi-squared is calculated, it's a difference squared, which is not going to be negative, and then divided by the expected. So a chi-squared statistic, if everything was perfect, it would be 0. If there was no difference between our actual observed and our expecteds in every cell, then all those terms would be 0, and you'd get a chi-squared of 0. Perfectly unassociated. So things will only ever be 0 or positive. And so again, we get this kind of hump on the left and only have a right tail, somewhat similar to what we saw with the MAD. Okay, so what was our chi-squared when the computer did it was 7.398. So what's the likelihood of getting that as a chi-squared? And notice we get a slightly different p-value. These are conceptually different statistics. right? One is just taking differences, another one's taking differences squared as a percent of the expected. So you aren't going to get the same p-value here for the two statistics, but when one is quite small, the other one should be quite small. Notice we have about twice the p-value now, but still a significant p-value at the 5% level, not significant at the 1% level. So at the 5% level, we would feel confident saying there is an association between how the vehicle arrives and whether or not it comes to a complete stop. At the 1% level, we would not be willing to say that. This shape we're seeing up here is called the chi-squared distribution for obvious reasons, because it comes from a chi-squared statistic. Here's the graph of it, by the way. We are simulating it, but there's the actual chi-squared distribution, the mathematical model, if you will. And that's what the theory will be based on. All right. So again, it's a similar concept. You just shuffle the expected value, or excuse me, the explanatory and response variables so that if there had been any association, it's gone because we've just shuffled it. And so you get the distribution of the types of things you would see if there was no association. And then you, as always, calculate what's the likelihood of getting what we got or something more extreme. And that's your p-value there.